Hey, what's up guys? So recently I was working on a temperature sensing project, and while I was doing my research for that, I discovered the LMT01, and this was really the perfect sensor for this application. In fact, I love this sensor so much that I've been putting it into all of my other projects. So you can see it's very accurate, 0.5 degrees C, only 2 pins. It's digital, so I don't have to introduce more inaccuracies by measuring anything on one of my analog inputs. You just have to measure the digital pulses out of it, and we'll get into how all of that works here in a little bit. It's also great for battery powered applications because it's not only low current, you can see 34 microamps, and we'll get into that again later on, but it's also pretty fast. So the time it needs to measure the temperature and output those pulses is pretty fast. So I decided to make a whole video dedicated just to this sensor, and we'll get into how to work with it on an Arduino as well as the ESP8266. So here I've got one hooked up to one of my little trig boards here, and I've had this outside posting to a Slack channel once an hour. So check this out, it's kind of cool. Here it is. So I've got a Slack channel called Log, and once an hour the board wakes up from a sub 1 microamp sleep state, grabs the temperature, and posts it up here. So out here on the East Coast, you can see it's pretty darn cold. We hit -3 degrees Fahrenheit. Yikes. And then here we are indoors at 71.2. So not bad. So anyway, let's go ahead and get into how this sensor works. Okay, so if we take a quick peek at the data sheet here, I'm just going to scroll down a little bit. And, you know, by the way, the accuracy, even though they state 0.5 degrees C, it's probably going to be much better than that if you look at this chart. That's just the worst case. But anyway, if you kind of scroll down here, what I'm looking for is to show you how it actually outputs those pulses. It only has 2 pins. So you've got a VP pin and a VN pin, and this is the hardware setup. So you power it up through the VP pin at, I'm using 3.3 volts. Of course it can run at 5 volts as well. And what it actually does here is change its current. Okay, so in other words, its source current changes and you're measuring that. So kind of complicated, but if you look here at the timing diagram, scroll down, you see that a high pulse here is 125 microamps of source current to the device. A low is 34 microamps. So if we feed that down through a shunt resistor of 10k ohms, so if your current from the 3.3 there goes down here, we're going to generate a voltage right across this 10k ohm resistor. So again, if it were high, we're going to be at 125 microamps. That times the 10k will give us a voltage right here of 1.25 volts. The low part of that, which is actually what the part actually needs to run, is 34 microamps. So that times the 10k is 0.34 volts. So we're going to have these 2 voltages on that 10k ohm resistor, and we could basically feed that right into an analog pin if we wanted to. We could, if we could sample it fast enough, we could feed it into a comparator input if the microcontroller supports that. The Arduino ATMEGA processor does have comparator inputs, so you could do that, or you could just add a simple NPN transistor. So we're using the 2N3904. It will turn on at the high level, 1.25 volts. So it'll actually turn on, and it pulls this pin here low. And when it's off at the 0.34 volts, the 10k ohm resistor right there snaps it up high to 3.3 volts. And that's all there really is to the circuit. And I have that exact thing set up right here. So you see we've got 3.3 and ground going over here, and the 3.3 is feeding the VP pin here directly, it also acts as a pull-up for the 10K over here. Of course, we have ground going over there, and then here is the digital pin right here. And this has to be an interrupt pin on the ATMEGA. And that's the way I'm doing it. Now, I did not use the comparator on the ATMEGA, and the reason for that is because I wanted to use my same code for this, everything exactly, for the ESP8266. Because I'm already on this board here using the analog input for the battery voltage monitoring. Okay, so anyway, that is pretty much all there is to it. And then once you get the pulses, if we scroll down here, you see the little formula here, so pulse count, and that's exactly what we have in the code. So we plug in the pulse count here and we get the temperature output in Celsius. So over here in my Arduino code, it's running right now. Here's my raw pulses. I'm actually looking at degrees C converted to Fahrenheit, and then keeping track of the high and low, showing the differential there, and that's mostly just test code. And of course, I'll make all of this available for download. We'll go through this code too, by the way. So before we do that, though, I do want to hook up a logic analyzer and just show you kind of how this whole thing is actually working. Okay, so I've got the Saley hooked up here, and I just wanted to quickly show you what to expect out of that circuit feeding the digital pin of the Arduino. So looking over here, I've already sampled that, and I'm powering the LMT01 directly from the 3.3, so it's going to continuously output that pulse train over and over and over again. You could actually drive it from another digital pin off of your micro if you wanted to conserve power. So let's say you wanted to deep sleep the microcontroller, then you may want to kill the temperature sensor completely and drive that pin low. So that is something you could do. In the case of the trig board over here, I actually kill the entire 3.3 rail when it sleeps, so it doesn't really matter, and I actually had to do that to keep the sub 1 microamp sleep currents. But anyway, so just looking at that, you can kind of see here that in a continuous conversion mode, it takes somewhere between, well, I think actually it's in the data sheet, but right here running 81 milliseconds there between conversions. And if we zoom in on one of these, you can see that the 10K ohm resistor keeps that pin high at 3.3 volts, and then as soon as we get a pulse, we pull that transistor low, and that's what you see. So in the Arduino, we're actually measuring these falling edges, and we could actually just verify that the readings are accurate, and I had to actually do this. Let me zoom out a little bit there, and then let's see, we'll add a measurement and look at falling edges, and then we can look straight across this entire thing, and you can see 1153, and when I sampled this, it probably was 1153. So, and of course that's all been verified. So anyway, just wanted to show you that, and we may actually poke around at some other things once we walk through the code. So let's go ahead and do that now. Okay, so here we've got the sample code that you just saw running there, and it's pretty straightforward. I kept it all in one single tab here just so that it's a little bit easier to download. All you have to do to roll this into your application is just hang on to the functions, the variables here. And if we scroll down a little bit, we've got the get temperature function and the interrupt handler for the pulse counter. But anyway, we'll get into all of that here. So let's just go right through this. So right up here at the top, the only pin we're going to define is the output pin from that circuit you saw feeding the digital input. And on the Arduino, we're using digital pin 2 because that is one of the interrupts we can use. It is D5 on the ESP8266. That's what I used, and I'll test that at the end and maybe get into some other stuff. I tend to ramble, so I'm just going to get right to the point here with the code, and then afterwards I'll just take a deep dive into some of the other cool stuff going on here. Anyway, going on here, the variables we're using, the pulse count, and that's what keeps track of the pulses. So every time the interrupt fires, we increment that pulse. It's got to be volatile because we are changing that variable in an interrupt. So we've got to tell the compiler that that could just change randomly in the code anytime that edge is goes low. So then, of course, we've got the temperature C, temperature F, temp high, temp low. You don't have to use any of those, though, if you don't want to. Functions, like I said before, we've got the pulse detect interrupt function, and then the main function that we call to actually get the temperature. It returns a float temperature in C. We're using the serial monitor for debugging, just printing out what the temperature is at 115.2. We're going to make that pulse pin an input. And then right here in the, and you might be wondering, well, where are you going to attach it to an interrupt? You'll see. So in the loop here, the only thing you really need to look at is this. Temperature C is equal to get temperature, because this is going to return the temperature in Celsius. Then all of this stuff here is just, to print out the high, the low, the converted temperature, differential, and the raw pulse count. So you can really just ditch all of that if you don't want it. You might be wondering, well, what's this check right here? Well, if anything goes wrong in here, it will return 1000. So if the temperature is 1000 degrees C, you've got bigger problems. So anyway, that's what I used as a fail. So let's just jump right into get temperature down here. First thing we do is attach the interrupt using this digital pin to interrupt. So this will set up digital pin 2. On the Arduino, it's actually interrupt 0, I think. So this just takes the 2 and convert it over to a 0. That's a new thing that I discovered built into the Arduino IDE, which, by the way, I'm using 1.8.3. And we're going to call this function, pulse detect function, down there on the falling edge. So down here, pulse detect right here. And again, the only thing we're doing in there is incrementing the pulse count by 1. Conversion time, we use this all over the place. Probably not the best name for that variable. And it's just going to grab the current millisecond count. And then we've got a couple while loops in here. So the first thing I wanted to do is, because this could get called at any time. So let's say it gets called, I'm going to zoom out a little bit here. Let's say it gets called right here. And you don't want to start counting the pulses here because you're going to get less than the total pulses out. So what that does right here, the first thing is just to make sure that we're not in the middle of an existing pulse train. So it goes ahead and actually just keeps track, and it's looking to make sure that the pulse count stays at 0 for at least 10 milliseconds. So if we look here, you've got the, if the pulse ever is incremented, set it back to 0 and reset the timer. So it actually just stays stuck here until it gets 10 milliseconds of silence on the pulse counter. I got this yield added in here, and that's for the ESP8266. And to be honest with you, some of the ESP stuff I'm still kind of figuring out, but it is my understanding that since we've got a full-blown Wi-Fi stack going on, and it has to keep the Wi-Fi radio happy, if you stick it in a while loop where it can't get out, you could crash it. So I've got the yield in there to let it take care of its housekeeping for the Wi-Fi. So once we get 10 milliseconds of silence, we go ahead and reset the pulse count back to 0, and we jump into another while loop. So while that millis minus conversion time is less than 150 milliseconds, we wait for a single pulse. So we're going to sit here and wait for the first pulse out of that pulse train. again, we've got the yield here. And as soon as we get a pulse, go ahead and break out of that. If we never got a pulse, we return 1,000. So that was a fail. Then we reset the conversion time again. So we've got our first pulse. Then we're going to keep track of the old pulse count. So I've got a new variable here. I'll explain that in a second too. And we also have pulse time. I'll also explain that. So for now, just we jump into another while loop here. And this one stays stuck in here for 60 milliseconds. So let me go back here to the logic analyzer. So let's say we want to grab our measurement right here. We wait for 10 milliseconds, we're quiet. Then we wait for 150 until we see our first pulse. And as soon as we see that first pulse, we're going to wait it out 60 milliseconds for the entire pulse train to come through. In fact, all of this too, by the way, if we go in the data sheet here, they've got some of these timings somewhere in here. Actually, that was probably it. This T data and T conversion. Yeah, they're up here. So you can see temperature conversion time on power up would be 50 milliseconds. The T data transmission time is 47 milliseconds. And I think that's about it. I think there's one more in here somewhere. Yeah. Oh, here it is. Duh. Okay. So right here. So you've got 104 milliseconds max between total measurements, and then you'll have 50 milliseconds for an entire pulse train. So that's where some of those timings came from. And I'm giving some safety margin in each of them. But it really doesn't matter because I added some cool stuff in here to take care of that. So in here, basically, we could just stay stuck and measure the total pulses. So we've already got the first pulse, okay? And then in here, we're going to continuously get hit with pulses for 60 milliseconds. And that's fine, and I thought that was cool. But the problem is that it'll stay in there for 60 milliseconds. But look, just that measured time alone was only 14 milliseconds. So if I've got a battery-powered application, all of that 60, let me show you what that looks like. I'm going to put a time right there and then right here. So 60 milliseconds would be all the way out here. So this time here is just wasted battery. So basically what I wanted to do was keep an eye on that pulse count time, and if it goes idle, go ahead and break out. We're done. We've got all of the pulses out of the sensor, and that's what this takes care of. So every time we have a new pulse, we check it. We see, oh, it's not equal to the old pulse count. Remember this variable here, which grabs the existing pulse count. We've got a new pulse, just came in. Set the old pulse count equal to the new pulse count, and then grab a timestamp of that for the pulse time. And then if we get stuck in here and we haven't had a pulse count for a while, if that time ever is greater than 5 milliseconds, then we know for sure that we're idle. Because if you take a look here, we'll zoom in a bit. Let's see if we can look here, and I'll just throw down the timing here between just one period here. You know, that's only 11.2 microseconds. So, yeah, let's escape out of that. There we go. So if we look at what 5 milliseconds would be, go here. Okay, we gotta go zoom way out actually. Yeah, 5 milliseconds would be all the way out here. So, I mean, that's still quite a bit of dead time, but it's only 5 milliseconds. So, guarantees that the pin has gone idle and we can break out. So that's what that does. So we're stuck in here counting pulses, keeping track of the time basically in between those pulses. And if we don't get a pulse and our time has elapsed 5 milliseconds, then break out. And that's what that does right there. If our pulse count is ever less than 5, we know something went wrong there. So return 1,000. In fact, every once in a blue moon on the ESP8266, I think it was, I would get a little bit of noise. And that little bit of noise on the line was enough to trigger the first pulse. So I would have like a pulse of like 1 or 2, which obviously isn't right. So that's when I decided to put this little test in here and go ahead and return 1,000, bail out. Then I just detach the interrupt because we're done with it in this function, and then convert the pulse count into a temperature. And this is straight out of the data sheet, 7.3.2 in the data sheet, and return that temperature in degrees C. And that's all the code, actually. So now let me show you a couple cool things. Okay, so basically what I'm doing here is kind of an interesting test because I've got digital pin 3 here set up as an output now, and that's just going to go to the Saley for debugging, just to show, you know, what the Arduino is sort of doing, because right now we're just looking at the temperature sensor that's just free running. So we'll drive that pin high when we go to get a temperature, and then low when we're complete. And this is just running as fast as it possibly can. There's no delay in there at all. Oh, there's a random delay. I forgot I actually added that. So cool. Okay, so when it gets a reading, I forgot to mention this in the code actually. So when it gets a reading, it actually does a for loop of a random delay here between 50 and 200 milliseconds. So the reason for that is just this. I wanted to show you this. So this is kind of cool. This is the sample. This is that digital pin 3 below. This is the output straight from the sensor. And if we zoom in here, this looks crazy because look, it doesn't take that long to get a measurement, but because we're going so fast and we require the 10 milliseconds, you can see here that when we went to go request it, this time here, and this would have been the 10 millisecond point right here. So 10 milliseconds is kind of a lifetime because I could have reduced that down to like 1 or 2 milliseconds actually, but since I'm waiting 10 milliseconds, I crashed into the pulse train, so it wasn't long enough, so it waited for the next one. And then right here is when it actually started measuring. And we can look at that over here. I'm just going to pop that down right there and then look at the first one. So you can see that this is actually where it actually grabbed the pulse train. And then when it stopped, we had about 6 or so milliseconds after. So that wasn't really on that line. So let me pull that over a bit. Still pretty close to 6. So, and that's where that should have been 5 milliseconds, the 5 millisecond timeout. So that's kind of cool actually. And that's what I wanted to show you here is how that works. So these skinny ones in here, that's when I was able to fully get a 10 millisecond duration of silence. Let's see, it was pretty close, 10 right there. So I got my 10 milliseconds and then I went right in and got my pulse train and then got out. So that's sort of the ideal measurement right there. But either way, it does work and it is still pretty fast. So I mean, even in some of these, I had to wait 187 milliseconds for the, I'm looking at, never mind, don't look at that. Let's see, right there to right there. So about 110 or 111, no, what is that? 116 milliseconds I had to wait total for that measurement. And that could be optimized. So anyway, wanted to show you that. Let's get into the ESP8266 real quick. Okay, now I have the same setup with the ESP8266. Everything is the same, and if we look here at the trig board, I'm using GPIO 5 hooked over to it, and that's to the output of that circuit to the digital pin GPIO 5. I needed ground as well, and then 3 is on the other side, and this is just sort of air wired over. And again, I sort of hacked all of the resistors and the NPN transistor down here on the board, and that was a little bit cleaner than with all the wires like you see here. But anyway, so looking over at the code, the differences for the ESP8266 are pretty straightforward. You've got the pin, obviously you have to change to 5, but also, and this is kind of interesting, is you have to add this to your interrupt function. And when I did not have that originally, I was getting random crashes. All of a sudden, I would crash and it would not recover. So I did a little bit of research and found on some forum somewhere that you should place this on all of your interrupt functions. And I believe it has something, and again, I'm still kind of getting up to speed with some of the ESP stuff, but it has to do with the way the instructions are executed. And on the ESP, you know, you've got the SPI chip on there, and it's actually running out of that SPI chip. So I guess when the interrupt calls, this allows you to put this instruction or this function into its onboard memory, the instruction cache RAM, I think, okay? So now it's just a little faster, I guess a little easier for the ESP to get to instead of running that out of the SPI flash. Again, that could be totally wrong, but either way, this is needed to run this. And it will run without it, but again, it did occasionally crash on me without it. So that's pretty much it for the LMT01. Kind of a cool sensor. I've been using it on several projects. I like it better than the DS18B20 right now. May not be the perfect replacement for that part. You can't run it on as long as a cable. You can only have one sensor on a cable. With the DS18B20 you can have several because it's more of a one-wire bus. And there's some other advantages, disadvantages, but right now it's kind of a cool sensor, so I thought I'd make a video about it. Anyway, that's the video. Thanks for watching.